So let's start with what we do know. We know that about 13.8 billion years ago, the universe was incredibly hot and incredibly dense. Everything, all the matter, all the energy, all the space itself was compressed into an extraordinarily small region. And then it started expanding. We call this the Big Bang, though that's kind of a silly name because it wasn't really a bang at all. There was no sound. There was no air for sound to travel through. It was more like everything started rushing apart, and it's been doing that ever since. Now, how do we know this? Well, we can see galaxies moving away from us. The farther away they are, the faster they're moving. That was discovered by Edwin Hubble. And by the way, when I say see, I mean we look at the light from these galaxies, and we see that it's shifted toward the red end of the spectrum, stretched out by the motion, like the sound of a car driving away from you drops in pitch. So we can work backwards and figure out that everything must have been much closer together in the past. We also found this thing called the cosmic microwave background, and that's really beautiful. It's like an echo of the Big Bang. About 380,000 years after everything started expanding, the universe had cooled down enough that electrons could stick to nuclei and form the first atoms. Before that, the universe was like a thick fog. Photons couldn't travel very far without bumping into something. But when the atoms formed, suddenly the universe became transparent. The light that was released at that moment has been traveling through space ever since, and we can detect it today. It's everywhere, coming from all directions, with a temperature of about 2.7 degrees above absolute zero. That's remarkable evidence. But here's where it gets tricky. When you try to work backwards and ask what happened before the Big Bang, you're making an assumption about time. You see, according to Einstein's general relativity, space and time aren't separate things. They're woven together into what we call spacetime. Matter and energy curve spacetime, and that curvature is what we experience as gravity. Now, if you use Einstein's equations and work backwards, you find something very peculiar. You find that as you go back in time, everything gets more and more compressed, hotter and denser, until you reach a point where the mathematics breaks down completely. We call that a singularity. At the singularity, the density becomes infinite, the temperature becomes infinite, and the equations start giving you nonsense, infinities everywhere. And according to this picture, time itself begins at that moment. So when you ask what came before, you're asking about before time existed. And that's like asking what's north of the North Pole. It doesn't make sense. If time itself began at the Big Bang, then there is no before. The question doesn't have an answer because the question itself is based on a faulty assumption. But wait, before you think that's the end of the story, let me tell you why most physicists, including myself if I were working on this today, don't actually believe in that singularity. Here's the thing. We know Einstein's general relativity is not the complete picture. It's a wonderful theory. It explains gravity beautifully at the scales we can observe, but it's a classical theory. And we've known since the 1920s that the world isn't really classical, it's quantum mechanical. What does that mean? Well, in quantum mechanics, things don't have precise values until you measure them. A particle doesn't have a definite position and momentum at the same time. There's an uncertainty built into nature itself. And at the incredibly tiny scales near the Big Bang, I'm talking about distances smaller than a proton, times shorter than a trillionth of a trillionth of a trillionth of a second. Quantum effects become crucial. The trouble is, we don't have a complete theory of quantum gravity yet. We can do quantum mechanics and we can do general relativity, but putting them together in a consistent way. That's one of the great unsolved problems in physics. There are various attempts, string theory, loop quantum gravity, and others, but we don't have the answer yet. And this is where things get really interesting, because these quantum gravity theories suggest that maybe there isn't a singularity after all. Maybe something else happens. Let me tell you about some of the ideas people are playing with. One idea comes from loop quantum gravity. In this approach, you imagine that space itself is not infinitely divisible. Just like matter is made of atoms, space might be made of tiny discrete chunks. There's a smallest possible volume, a smallest possible area. It's fantastically small, about 10 to the power of minus 105 cubic meters, but it exists. Now, what happens if space is like this? Well, imagine you're compressing the universe backwards in time. In Einstein's theory, you can keep compressing forever until you reach infinite density. But in loop quantum gravity, when you try to compress space beyond a certain point, something remarkable happens. The quantum nature of space creates a kind of repulsive force. It's like trying to compress a sponge. At first it squeezes down, but when it's fully soaked, it can't absorb any more and pushes back. This suggests that instead of a Big Bang singularity, you might have a big bounce. The universe could have been contracting before our Big Bang, got compressed down to some incredibly tiny but finite size, and then bounced back into expansion. Our expanding universe might have been preceded by a collapsing one. Time doesn't begin at the bounce, it extends through it. Now that's a beautiful idea, but here's the catch. What can we observe to test it? If there was something before the Big Bang, can we possibly know anything about it? This is where things get philosophically tricky. You see, during that incredibly hot, dense period, everything gets scrambled. It's like trying to read a message that's been through a shredder, then burned, then the ashes mixed together. How much information could possibly survive? Some researchers think maybe gravitational waves from before the bounce could make it through. Others think we might see traces in the cosmic microwave background, but we're not sure. There's another wild idea called conformal cyclic cosmology, proposed by Roger Penrose, brilliant physicist, won the Nobel Prize. He suggests that the Big Bang wasn't the beginning, but rather a transition point between an infinitely old expanded universe and a new one. In his picture, the universe goes through infinite cycles. Each cycle starts with something like a Big Bang and ends when the universe has expanded so much that all the matter has decayed into radiation. At that point, in a sense, there's no way to measure distance or time anymore, and that becomes the Big Bang of the next cycle. Then there's the idea of eternal inflation. According to this, our Big Bang was just one of countless little bangs happening in an eternally inflating super-universe. Imagine a pot of boiling water. Bubbles form, expand, and pop. Each bubble could be a universe like ours, with its own Big Bang. Before our Big Bang, there was just more inflation, and before that, more inflation, possibly stretching back forever. There are also ideas from string theory about colliding branes. These are like higher dimensional membranes floating in an even higher dimensional space. When they collide, boom, you get a Big Bang. Before the collision, the branes existed separately. Now, I want to be honest with you about something important. All of these ideas, the Big Bounce, conformal cyclic cosmology, eternal inflation, colliding branes, they're speculative. They're educated guesses based on our best understanding of physics, but we don't have direct evidence for them yet. Some of them might never be testable, and that's a problem, because in physics, if you can't test it, if you can't make predictions that can be verified or falsified, then you have to be very careful about calling it science. But here's what I think is remarkable. Even though we don't know what came before the Big Bang, if anything came before, we can still study what happened immediately after, and we're getting very good at that. We can understand the physics of the universe when it was a second old, when it was a microsecond old, even when it was a trillionth of a second old. The fact that we can do that we can understand the universe under such extreme conditions, that's extraordinary. And here's something else that's profound. The question, what came before the Big Bang, forces us to think carefully about what we mean by causation, by time, by existence itself. In our everyday experience, everything has a cause. Time flows from past to future. Things exist in space. But maybe at the very boundary of the universe's existence, these concepts break down or take on different meanings. You see, when you get to the Planck scale, that's about 10 to the minus 43 seconds after the Big Bang, space and time themselves become quantum mechanical. They start fluctuating, creating what John Wheeler called quantum foam. Imagine space-time not as a smooth fabric, but as something that, when you zoom in far enough, looks like foam, full of bubbles and tunnels and bridges appearing and disappearing. At that level, our normal ideas about cause and effect don't work anymore. The future can affect the past, or rather those concepts don't even apply. So maybe the right answer to what came before the Big Bang is that it's a category error, like asking, what does blue smell like? The question assumes that our normal concept of time applies, but maybe it doesn't. But, and this is important, maybe it's not a category error. Maybe there really was something before and we just haven't figured out the right way to ask the question yet, or developed the right theory to answer it. You know what fascinates me about all this? It's that we're even able to ask these questions scientifically. 100 years ago, the Big Bang was considered philosophy or religion, not science. Now we have actual data. We can measure the cosmic microwave background to exquisite precision. We can observe gravitational waves from colliding black holes billions of years ago. We can simulate the evolution of the universe on supercomputers. We've pushed the boundary of scientific knowledge right up to the edge of existence itself. And we're not done. There are experiments being planned, observations being made, theories being developed. The James Webb Space Telescope is looking at the earliest galaxies. Gravitational wave detectors might someday detect ripples from the Big Bang itself or from before it. Particle accelerators are probing physics at higher and higher energies, getting closer to the conditions of the early universe. Here's what I really want you to understand. The beauty of physics isn't just in the answers. It's in the questions and in the process of trying to answer them. When we say we don't know what came before the Big Bang, we're not throwing up our hands in defeat. We're acknowledging the limits of current knowledge while actively working to push beyond those limits. And there's something deeply human about that. We're these tiny creatures on a small planet, orbiting an average star in a galaxy that's one of hundreds of billions, in a universe that might be one of infinitely many, and yet we have the audacity to ask, how did all this begin? What came before? Why is there something rather than nothing? The fact that the universe is comprehensible at all, that it follows mathematical laws we can discover and understand, that's miraculous in itself. Why should the universe be understandable? Why should our brains, evolved to hunt antelope and gather berries, be capable of figuring out quantum mechanics and general relativity? There's no obvious reason, and yet here we are. Let me give you an analogy that might help you think about this. Imagine you're watching a movie. You start the movie at the beginning and you follow the story. Now imagine running the movie backwards. The story makes less and less sense as you go back until you reach the very first frame. What came before that first frame? Well, maybe nothing. That's where the movie starts. Or maybe it's a sequel and there was an earlier movie. Or maybe the same footage appears in a loop, and if you go before the beginning, you just find the end of the loop. Or maybe the question doesn't make sense because before the movie is like asking about events that aren't in the movie at all. The universe might be like that. Our Big Bang might be the first frame, or it might be part of a larger story, or it might be one of many movies being shown simultaneously in different theaters, or the question itself might not apply. The honest truth is this: we're still writing the equations, still doing the experiments, still arguing about the interpretations, and that's okay. That's how science works. We don't pretend to have all the answers. We're comfortable with uncertainty, with not knowing, because that's where the interesting work is. What I can tell you with confidence is what we don't think happened. We don't think the universe popped into existence magically with no explanation. Every quantum gravity theory that's been proposed has some explanation for the transition, whether it's a bounce or a branching from eternal inflation or something else. The universe appears to be self-consistent. If there was a before, it would connect to our after through physical laws, not magic. We also know that whatever happened at or before the Big Bang, it left traces. The cosmic microwave background isn't uniform. It has tiny fluctuations, tiny temperature differences from place to place. Those fluctuations are the seeds that grew into galaxies and stars and planets and us. The pattern of those fluctuations tells us something about the very early universe, possibly about a period of rapid expansion called inflation that happened in the first tiny fraction of a second. And if we can learn about that, maybe we can learn about what came before. So here's where we are. We know the universe has been expanding for 13.8 billion years. We know it was once incredibly hot and dense. We know that our equations break down at the very beginning, which suggests we need a better theory. We have candidate theories that suggest various possibilities for what came before, if before even makes sense. And we're actively working on ways to test these ideas, or at least to constrain them with observations. That's the state of the art. That's where human knowledge currently ends and speculation begins. And you know what? I think that's beautiful, because it means we haven't figured everything out. It means there's still work to do, still mysteries to solve, still discoveries to be made. If someone tells you they know what came before the Big Bang, be skeptical. If someone tells you it's impossible to know, be skeptical of that too. People said it was impossible to know what stars were made of until we figured out spectroscopy. If someone tells you the question is meaningless, Maybe they're right, but maybe we just need to reformulate the question in the right way. The point is to keep asking, keep thinking, keep testing. That's what science is. It's not a collection of facts. It's a method for finding things out. And right now, the question of what came before the Big Bang is at the very frontier of that method. You know, when I think about this question, I'm reminded of why I fell in love with physics in the first place. It's not because physics gives us comfortable answers. It's because physics forces us to confront reality as it actually is, not as we wish it were. And reality, it turns out, is stranger and more wonderful than anything we could have imagined. The fact that space and time aren't absolute, that they can bend and twist and maybe even end, that's bizarre. The fact that quantum mechanics says particles can be in multiple places at once, that observation affects reality, that's weird. And the fact that we don't know if time had a beginning or if our universe is alone, that's humbling. But it's also exhilarating, because it means reality still has secrets. It means we haven't reached the end of understanding. It means there's still work for future physicists to do, still puzzles to solve, still phenomena to discover. So when someone asks me what came before the Big Bang, I tell them, we don't know yet. We might never know, or we might figure it out next year. We have ideas, beautiful, mathematical, testable ideas, but we need more data, more theory, more clever insights. And in the meantime, isn't it wonderful that we can even ask the question? Isn't it amazing that we can push our understanding right to the edge of existence itself and say, we've come this far, let's see if we can go further. That's the adventure of physics. That's what makes it worth doing. Not knowing all the answers, but knowing how to ask the right questions and having the tools to search for answers. And who knows, maybe someone watching this, someone young, someone curious, will be the one to figure it out. Maybe you'll develop the theory of quantum gravity that finally explains the Big Bang. Maybe you'll design the experiment that detects traces of a previous universe. Maybe you'll have the insight that makes it all click into place. Or maybe, and this is just as valuable, maybe you'll discover that the question needs to be asked differently, or that it leads to an even deeper question we haven't thought of yet. That's the beauty of science. Each answer opens up new questions. Each solved mystery reveals deeper mysteries. And the greatest mystery of all, why there is something rather than nothing, how it all began, what came before, is still out there, waiting for us to figure it out. Or maybe not to figure it out completely, but to understand it a little better than we do today. And that's enough. That's always enough. Because the joy is in the journey, in the process of discovery, in the moment when you suddenly understand something you didn't understand before. So that's my answer. What came before the Big Bang? We don't know, but we're working on it. And it's one of the most exciting questions in all of science. And if that's not a satisfying answer, well, maybe you should become a physicist and help us figure it out. Thank you.